So as Kath said, that's the title of my project, and I guess when we're talking about advanced technologies, we sort of looked at a few different things, including trialling some sensors and using the hyperspectral imagery. But the focus I'm going to talk about probably in this talk mostly is about the productivity, mineralisation and things like that, which I'll explain. So I would like to also acknowledge the funding from the government and also from Dairy Australia, and the University of Melbourne has also contributed funding into this program as well. This is the team. So at the top there we have Oksana Belyeva, who was the lead researcher in the project, and Graham Ward, who pretty much did everything, but was the key in being a centrally located dairy expert in the region, which made our trials run very, very smoothly. We have Delhi and Jim, who are advisors into the program, Professor Yong Lee, who helped us with the mineralisation calculator. We had some remote sensing people, Alexis Pang, Manish, who is shown in the photo taking some measurements, and Dongril Ru from engineering, and a few other people, Arjun Pandey, who is going to present on Thursday actually, on the N2-N2O ratio work that he did. We had a master's student, Tord, looking at mineralisation, and we had a research assistant and an analyst, and also lots of other people helping. So there's always a big team going out there to help. And I haven't acknowledged in here the dairy farmers, which I should acknowledge those, which is the Croft family for our primary site, and the Powell family helped us with another site. And they were very generous because we were at the sites for almost 3 years. So in terms of the objectives and aims for the industry, what this project was about was enabling growers to better understand nitrogen cycling to make better fertiliser decisions. So we wanted to understand the seasonal responses of pastures to nitrogen fertiliser in the high rainfall zone of Victoria, and what we mean by high rainfall zone is around 800 millimetres, because I realised just now that I'm in Queensland, so it's quite different meaning. So it's about an 800 millimetre average rainfall, predominantly falling through the winter, that rainfall. We also wanted to look at what the fate of applied nitrogen fertilisers was and what the likely losses were. So we didn't actually measure these losses, but from our work looking at the fate of fertiliser, which used these 15N techniques that Dave mentioned before, we were able to understand what was missing and then make a prediction of where that had gone based on previous research and conditions at the site. We wanted to also understand the contributions of mineralisation to pasture nutrition, and we were particularly interested in this because there was a big question around what was happening in the autumn break, particularly in dryland systems down there. So after a dry summer, where we get the rainfalls coming through, people were unclear about how much nitrogen would be supplied into that pasture at that autumn break time. And so making a decision about whether to put fertiliser out or not was a big question for the industry in that location. We also assessed the suitability of urease and nitrification inhibitors to improve nitrogen cycling, but we used this in terms of using an approach where you would use an inhibitor that we knew was targeting the loss pathway at a particular time. So we didn't do either DMPP, which is a nitrification inhibitor, or one of the urease inhibitors. We used one or other of those across the year, depending on what loss we expected to be happening. And for our advanced technologies, here's the identifying the suitability of these remote sensing approaches when making fertiliser nitrogen decisions. So our questions were, how can we improve the nitrogen fertiliser use efficiency? How does the response of pastures to nitrogen change seasonally and annually, and why? What's the fate of the applied nitrogen, as I mentioned before? And with the mineralisation, we're interested to know how that occurs monthly, seasonally and annually, and also what were the key drivers so that growers would be able to understand what had been happening and make a decision based on that knowledge of how much mineralisation might have occurred to determine their fertiliser use. And while we know mineralisation is occurring, we wanted to get an understanding of how much of that soil nitrogen was contributing to the pasture nutrition compared to how much of the fertiliser nitrogen was contributing to the pasture nutrition at any particular time. And looking again at these urease and nitrification inhibitors in terms of NUE and productivity. All right, and also the question on the remote sensing approaches. So in terms of our research components, we had field trials, and our main site was located near Allensford in southwest Victoria, the high rainfall zone as we call it. And we had trials set up, small plot trials, as you can see on the right here, set up under an irrigated system and a dryland system on the same soil type. And that's where we did 2.5 years of measurements on irrigated systems. We actually only managed 1 year on the dryland because we had a terrible summer. So coming back to, I guess, to Lucas's point, that our pasture died out and we spent the next year trying to get it back up and realised that that wasn't going to happen. So we did go to another site to get another dryland set of data, which was in the region. We looked at a nitrogen response curve, so looked at applying nitrogen as urea top-dressed at 0, 20, 40, 60 and 80 kilograms of N per hectare. And then we used this, what we called an EEF program, at just 10, 20 and 40 kilograms of nitrogen. So based on the discussions so far, we chose lower rates to look at our enhanced efficiency fertilisers because we know that if any productivity benefit will come from them, it will come from applying them at a lower nitrogen rate. We did 15N studies, so you can see all those little chambers there set up in a row. That's some of our ones that we brought in from another site. So we ran these in various sort of guises over the experimental time period. And you can see there a picture of the engineers down with their drones. So we had a few different techniques looking at the use of the hyperspectral imagery. And that set of cores there, we realised that we were doing all our work on one field site and one soil type. So we had a bit of a look at 6 different soils that we brought in these chamber systems, in those PVC pipes there into the field to see what happened when we applied fertiliser into those different types of soils. So that was what the field trial looked like. So that's the irrigated site. We also had a urine treatment in there, but I'm not going to talk about the urine treatments. And all those little white crosses are related to the hyperspectral imagery collection, so don't worry too much about that. So it was just a replicated split block design experiment, and we had a similar setup on the dryland site as well. And each of those plots was a 3 by 3 metre size. We also did some laboratory studies, so we looked at mineralisation rates, and we also had our samples sent up to Phil Moody as part of that potentially mineralisable nitrogen measurements. And we did some work to look at the N2, N2O ratio in the lab relative to soil moisture, so we could relate that to some of our field N2O measurements. One of our aims was to develop what we called a mineralisation calculator, and this was designed to help growers, or as a tool that could be used by growers to make predictions about how much nitrogen they would get from mineralisation in their soil type, depending on what time of the year they were looking at, what the conditions had been prior to that time, what their carbon, what their nitrogen inputs were. So we had this mineralisation calculator developed by Young, and in the process of that we were able to identify the key drivers of mineralisation in this region as well. So I'll look at that later. So coming to the outcomes, we did see a clear seasonal response. Now I'll just say that these summer, autumn, winter, spring responses are averages for each of those seasons. So when we look at them as an average for the season, which is 3 months, we get these sorts of shapes, and this is for an irrigated system. So the summer response is obviously the strongest because we've got water and heat there growing the pasture. And so we are seeing a nitrogen response across those different seasons. The thing that we were particularly interested in, though, was this autumn break response. And so at that autumn break response, we saw that was often flat. And in 2017, we took a couple of measurements through the April. In 2018, we did a measurement in April and it was all flat. And so we were coming up with a great conclusion about this flat autumn response. That means that we need to manage nitrogen at that time differently. And then in April 2019, we got this really nice response. So it sort of threw our theories a little bit sideways. And what we discovered in that April 2019 was actually that we had more water deeper in the profile. So if we were measuring our water in the 0 to 20 centimetres, it was similar across those different times, but the water below that depth, which we might have traditionally thought was deeper than the roots of the ryegrass would be, was what seemed to be the difference between whether we got that good response in autumn. And so this is important for the industry because this is, if we're using an irrigated system, this data is for the irrigated systems. If we're using an irrigated systems in those regions, often the irrigator is turned off earlier to prevent the soils becoming too wet through the winter because they're duplex soils as well, so they've got the potential for the profile to fill up above the clay subsoil. And so if the irrigator is turned off too early to prevent that soil being wet through the winter, there's a potential that there's not enough moisture in the profile deeper down to support that response in autumn. So that was a thing that we believe is worth considering when people are managing nitrogen at that time. The second outcome is that we found that soil provides a large proportion of the pasture nutrition. So we did these 15N fertiliser studies like Dave's talked about, and we're just going to show some data here for both the dryland and irrigated sites for 1 month. So this is after we've fertilised, we do a harvest 1 month later, looking at the nitrogen recovery. So I've just put in there the biomass production, so you can see much lower production at this I think was a 2018 experiment. So we had these flat responses in autumn and good responses in spring, much more production. If we looked at the nitrogen that was actually recovered in the plant, so of the fertiliser that we applied, how much ended up in the plant, we got in this 20 to 30% range, regardless of the rate of nitrogen that we'd applied and regardless of the season in which we were applying it. So there was similarities across there. If we looked at the nitrogen derived from the fertiliser, then we do start to see some differences, which is an indication of differences of nitrogen uptake by the plant. So we had greater nitrogen uptake by the plant in spring, and so we had, particularly at the higher levels, when we're putting on the 80 kilograms of N per hectare in spring, we're getting a much more of the nitrogen in the plant from the fertiliser because that's readily available, and we're getting that positive response curve, so we're still getting more nitrogen taken out of the system at those higher rates. And then at the lower rates, I guess it was quite similar in terms of the different seasons. And then I've just sort of highlighting this, that, you know, if we think about Dave talked a little bit about mineralisation. If we're thinking about that, then we can see that the nitrogen that's coming from the soil, as opposed from our fertiliser, is a large component of the soil, of the nitrogen nutrition of the pasture. And higher as we apply lower rates, because there's less taken up from that smaller amount of fertiliser that's applied. Yep. So that's the finding after one growth cycle. So immediately after fertiliser is applied, this is what's happening in the plant. So we had these 15M microplots that we'd put in. We applied the fertiliser, we harvested them after 1 month growth cycle, and they were the results I just presented. And then we left those plots in the ground for between 8 to 12 months, 8 months after spring, 12 months after autumn, and we progressively harvested the pasture every approximately month, every grazing cycle. And then at the end of the 8 to 12 months, we took the soil out to see how much was left in the soil. So here's our total recovery in the plant over that time period. So we're getting around about 40%, 30 to 50% higher recovery in the high rates on the irrigated pasture, because we're getting a lot of good production over the summer. It's continuous growth in that irrigated pasture, so that's one thing you should keep in mind, that is under irrigated pasture growth will occur all the time. Under the dryland system, the pasture growth is only occurring from the April to early November time periods. So then when we brought that up and looked at what was in the soil, we found that we have still got quite a large amount of our fertiliser has been retained in the soil, ranging from 27 to about 60, almost 60% in that system. And if we look at the total recoveries here, we can see that they range from about 60 to very high percent recoveries if we're considering the system as a whole, not just what's taken off from the plant. And the thing that I'd like to point out here is with the dry land system, that's the one that has produced our lowest recovery in autumn under the dry land system. And I feel that we know that that autumn is a key time when you could get ammonia volatilisation in these pasture systems. So in a dry land system where there's no water being applied to wash the urea in, there is a potential that you can lose substantial amounts. And we've measured about 30% nitrogen loss off other trials. So that low recovery in that autumn application of nitrogen after this 12-month period in the whole system could be due to that ammonia volatilisation loss that occurs at the start. The losses that would be happening in spring would be primarily due to that denitrification and leaching losses that would occur. As I said, we got 6 other soils in because I thought we were just focusing on this one site. We thought, let's have a look and see what happens if we get some different types of soils from around that high rainfall region. So we picked up some different soils with different textures. They're all on the acidic side and a range in organic carbon. And this is the average for the 0 to 20 centimetres, this data that's presented. What we found is that actually there wasn't a lot of difference in the total recoveries. I mean, there's a little bit less recovery in this than we were getting in the Allensford, but we haven't really been able to see a big difference between like any particular soil property type that was leading to a difference in the recovery from those systems. And this is from the spring application of that fertiliser. Okay, so we looked at mineralisation, and this is the pattern. This is modelled mineralisation based on our field data, based on 19 years of data for the site, for the climate data from the site. So this is done by Yong Lee. And we see this pattern of mineralisation over the year with high mineralisation rates in summer and much lower mineralisation rates through winter when it's colder. And this is the pattern for irrigated. With dryland systems, we get a very similar pattern, but there's just a slight change in the levels of some of those things at different times of the year. So we predicted that we could get 180 to 200 kilograms of N per hectare coming out of that mineralisation process, which was about 1% of the organic nitrogen pool, we estimated. We then, through this modelling process, Yong was able to identify the drivers for mineralisation. So he did some structural equation modelling and picked up these key factors: nitrogen rate, soil properties, future rain that's going to occur. This is about autumn. So how much nitrogen is going to be available at the autumn break from previous months, and how much will be available through that first growth cycle in autumn. So future rain is important, future temperature, but also past rain and past temperature were considered important. And for the mineralisation that occurs during the autumn, so after we've applied the fertiliser, for example, in that April time period, the ongoing nitrogen rate that we've applied over the past pasture management is important. The future temperature will influence how much mineralisation occurs. The soil organic carbon will be important, and also the past rainfall in terms of the system being in a state that's enabling it to have that mineralisation. So the organic carbon and the nitrogen rate are building that pool that's available, as well as with that biomass production from the past rainfall. If we look at the residues, then past temperature, how much nitrogen's gone on in the irrigated system is important. And in the dryland system, the past rainfall is very important, because if there's a good summer, we get pasture growth which uses up all the nitrogen that's produced over the summer by mineralisation. So that means there's not a lot of nitrogen available in the soil at the autumn break, because it's already been utilised by that growing pasture. If it's a dry summer, mineralisation will still occur and you'll get this available nitrogen produced, but it's not utilised by pasture because there is no pasture growing at that time. This is the mineralisation calculator that was developed, and this is specific for the region that we did our studies in. And Yong has set this up where he's identified, as you can see, the key predictors there, and he's established the model in a range of criteria suitable for the site, which is listed on the right there. And then it's possible, using this calculator, to shift where you think you should be by moving the arrows either way. And so from this model, it enables a prediction to be made of the mineral nitrogen available from residues, and the nitrogen that will be mineralised through the autumn break, and come up with a predictor. So it was a useful model, and we actually found it very useful in terms of, we discussed with growers a lot about the usefulness of this model, and we actually found it a really good tool for them to understand mineralisation in their systems, which was great. If we look at the remote sensing approaches, now this is the student Manish Patel who's been working on this, and he actually was looking at, were there different types of indices that could be used to predict nitrogen requirements in pastures. So that was the focus of his, rather than using current indices. And so he's produced a paper here that talks about some of those indices that could be used, and he's found some that seem to be better than the ones that are currently available that can make these predictions. And he's also looked at the benefits of taking measurements either right after harvest and at 4 different times of the growth cycle up to full harvest again, to see which of those times is better, and he will be publishing that one soon as well. In terms of the urease and nitrification inhibitors, we actually found limited benefit in our systems. We didn't think we had a high leaching loss. This is under-irrigated as well, so under-irrigated, the urease inhibitor is not really going to have any benefits because you're washing the urea in. And even going at the different nitrogen rates, by reducing our nitrogen rate, we still didn't find that there was a benefit. And these dairy soils down there have been in production for many years, so it's still possible that there's so much nitrogen in these systems that even, we can't get those efficiencies from that little change that's happening with these enhanced efficiency fertilisers because of the background. N2O loss we found was limited. Now, we only did a couple of snapshot times. It wasn't a focus of our project. So we did find a little bit of N2O loss, but we didn't consider it to be that significant. But we did, in the lab, we looked at the N2O to N2O ratios and found that at 60% water-filled pore space, we weren't really getting any emissions. And then at these higher water-filled pore spaces, so saturation and 80% of water-filled pore spaces, we could get this N2, so the N2O could be about 1 part to 9 parts of N2. So where we are measuring a little bit of N2, we have to factor in that where we're measuring a little bit of N2O, we have to factor in that the N2 emission could be 9 to 10 times higher than that loss in the system. Okay, so in terms of industry knowledge, this understanding of irrigation management around the autumn break and also potentially at the end of the growing season in dryland systems is important for maximising the nitrogen response and deciding whether to put out fertiliser. Use of fertiliser immediately may be quite small, but it's, as we've talked about before in some of these talks, because we don't want to end up mining the soil. So we know that the nitrogen is coming from the soil's organic pool, but we need to build that organic pool, and that can be through fertiliser application. And we can consider doing this at times when losses are likely to be less. If farmers can understand what the conditions are on their farm leading into the autumn break, they have a better understanding of how much nitrogen will come from mineralisation. So the people we talk to now have a better understanding of what will happen in a dry, average or wet year. In our systems that we studied, we didn't think there was much benefit from these inhibitor products. And with the remote sensing, they do seem to be developing these suitable spectra and indices and times for taking measurements. And finally, N2 dominates denitrification when the water content is high. These are our project outputs. So we've done a field days, workshops, industry forums, trainings and meetings. We've been contributing to some of the industry documents, presented at conference, got some publications happening and happened, and various other publications, and Graham's made a video there as well. Or Marguerite made a video with Graham in it, I think.